Hi, I'm Will. This is my Physics 2211 Lab 2 report. What is this lab? In this lab, we were supposed to cause a motion by dropping an object that would involve air resistance and see what resulted. In this, we use Tracker, which we use to get the actual data from our physical video, and we used a simulation through GlowScript code. Some of the main physics principles we will be talking about is stuff like the velocity update formula and how we can use this to calculate our net forces due to drag and whatnot. Also, here, a little preview. So first we have our position update formula. With our position update formula, we can see how we can get the position because we can get an average velocity, which we know is just the final velocity minus the initial velocity over our change in time. So therefore, we can calculate the position of our object as it falls down. Also, we need to use our velocity update formula. So for there, we can calculate the velocity of it going down because there is an acceleration due to gravity, which we need to account for. So therefore, that A is going to help us calculate our net force, along with F net can also equal our drag plus our gravity, which can give us the net force. If we look here, we can see that we do have air resistance in this lab composing, or not composing, but counteracting the gravity net force. So we have to calculate that in the force of air resistance, which would be our v times our velocity squared. In this, you can see our drop. We can see we have our object right here in the middle of the frame, which would be our system. And our surroundings are going to be everything like everything around it. So the air resistance is going to be composing and doing stuff onto our system. And our initial position was about top of this bed frame, which was about 6 meters. So here you can see we have a gravity force acting downwards, and then we have an air resistance force that is less, but still acting upon the paper, slowing its descent. In our code, you can see in this top section, we have the ball's position vector, which was initially 1.026 in the tracker software. And we have our starting time from when the ball was dropped, and then our time steps, along with the force due to gravity, which would be 9.8 meters a second, and the j hat, our unit vector for it. If we look on this last code, this is the code for one of our simulations we would in which we are calculating the drop without air resistance. So in this model, we can see we did t, and it's just multiplied by our gravity r vector, because that's the only thing that is acting on the force. Therefore, it is our net force, that negative mg. But if we look on the right, we can see we have b equals 0.0065, which helps us calculate our air resistance. Because the second model we computed had air resistance, and we need to calculate and see how R would fall with air resistance. So by doing that, we could use our coefficient in our net force, which would therefore counteract the gravity net force and give us our total net force. As you can see here is what the ball did in our simulations. Just went down with varying speeds and accelerations. Here's the first graph. This is just the graph of our actual data when we dropped it physically in the real world. Here's the tracker with no drag. As you can see, it goes negative. And then here is with drag. As you can see, the difference is that these go steadily to zero, but the bottom goes past sub-zero because without drag, it would go through the floor in the same amount of time that it took the regular object to go to zero because it has more velocity and it has more time. And some errors could arise in just video errors, logging our points in tracker, but for the most part, they would be negligible as we can see because the simulation and the real life were pretty close. Now, what does all this mean? Which model predicts terminal velocity? Well, both of our models actually predict that terminal velocity. And our terminal velocity, because it's just anything with drag. So if we look at our models with drag and without drag, the only model that will show terminal velocity would be the one with drag. Because to get a terminal velocity, it has to be the max velocity that it can possibly go. So basically, the gravity and the air resistance even out, and that gives us its max velocity, which is our terminal velocity. So therefore, only the simulation with drag would have terminal velocity. Now, what if the object was thrown downward instead of dropped? Well, our terminal velocity is going to stay the same. As you can see, this graph levels out, which means that we're reaching that terminal velocity. The only difference is we're going to reach it faster because it started out with a faster downward velocity. So it'll just reach its terminal faster. But terminal has to be the same because the air resistance and the force of gravity didn't change. Therefore, our net force is consistent. And that's my presentation. Thank you for watching.